Alrighty, welcome back to Fun Maths. In particular, we're talking about matrices and transition matrices today. So there's a little bit to consider here with this particular topic, so please bear with us. These are the things that you need to know. It says here, a Markov system is a system that investigates estimating the distribution of states of an event given the initial information. It also investigates the manner in which these stages change from one to the next according to fixed probabilities. So we'll have a look at how we can deal with that. When we go to illustrate these types of Markov systems, what we really mean is we're going to be creating a state transition statement. It could be a table or it could be a diagram, and they can be summarized in a transition matrix, which is denoted with a T. So for example, here is a statement and some examples of how you could set these out or illustrate them. So it says here, a group of delivery trucks transfer goods between warehouse A and warehouse B. They start at either warehouse and they finish the day parked at one of them as well. It says 70% of the trucks that start at A will park at A at night time or finish it there, and 30% will park at B. On the other hand, it says 60% of the trucks that start at B will park at B that night, and 40% will park at A. Alrighty, so obviously some will park where they start and some will park at the other spot. So you can represent that in the following diagrams. So you've got the transition statement, which we've had the chat about. You can also have like a table. So you can see here where they are going to and where they've come from. So if they've come from warehouse A, you can see that 70% or 0.7 will finish at warehouse A, which was from this statement here. Obviously, if they started or coming from warehouse A, and they will finish at warehouse B, there's 30%. We know we can check this out as well. These need to add up to 1 here as well. Likewise, from the information from the statement, if they start in warehouse B, so they're coming from warehouse B, and they're finishing at warehouse B, that's 60%, which is this one here, 0.6. And the last bit was if they started, or they came from warehouse B and they were finishing at warehouse A, that's going to be 40%, which is that there. Again, you can check that out. That column adds up to 1. Representing this with another diagram, you can see here if they're starting at A, 70% will also finish at A, or 30% will finish at B if they're starting at A, and you can follow the diagram around as well. Cool thing as well, you can put this information from a table or the statement or this diagram into a transition matrix as such, which looks very similar to the data that's in the table here. Alrighty. I've already sort of illustrated that each column of the transition matrix must add up to 1. We can see that each of those adds up to 1. Alright, these are the types of questions that you could be asked. It says, hey, represent each of the following as a transition matrix. Alrighty, so again, ultimately you just need the matrix here. Before we set it up, I would put like where they're coming from and where they're going to. So we're dealing with A and B here. Along the top it's where they're coming from, and along the side here it's where they're going to. So pulling up the information that we've got here, if you start or you're coming from A and you are going to A, it's 0.32. So we can fill that in. Likewise, if you're starting at A and you're going to B, it is 0.68. And you can check as well that adds up to 1, which is what we were looking for. Filling out the rest of the information, if you start at B and you are going to B, so B and you're going back to B, it's 0.55. And if you are starting at B, so you're coming from B and you are going to end up at A, it's 0.45. Again, that adds up to 1 there. Now, some people are tempted just to leave it like that. That's not the transition matrix, that's just putting it into a sort of like a table. The transition matrix for this data would be as follows. You'd have the 0.32 here and the 0.68 there. You'd have the 0.45 there and the 0.55 there. Perfect. Next one, you can have a worded statement again. Transition state, state transition statement. And you'd have to put this into a transition matrix. So again, what's this one go? Oh, cool, it's the train carriages. It says there are a number of train carriages operating between two depots. You've got North Depot and you've got South Depot. It says at the end of each week, 40% of the carriages that started at North Depot end up at South Depot, and 25% of the carriages that started at South Depot end up in North Depot. So we've got a little bit of information, so we can put in here. So again, you've got North Depot and you've got South Depot. South. Again, along the top, it's where they're coming from, and along the side, it's where they're going to. So it says at the end of each week, 40% of the carriages that started, so they're coming from North Depot, ended up at South Depot. So at this particular spot, it was 40% or 0.4. The next statement there spoke about the fact that 25% of the carriages that started at South Depot, so they're coming from South Depot, ended up at North Depot. Okay, so that there is 0.25. Now, there are some missing values in there. However, we just had the chat about how we can fill these out. We know that in a transition matrix, each of these columns needs to add up to 1. So we can fill those out when we write the transition matrix out. So putting it into a transition matrix, we got that from the statement. And filling in the gaps there. To make this column here equal 1, we know that this has to be 0.6. And to make this column here equal to 1, we know that this has to be 0.75. Perfect. Alright, let's have a look at the next information. Alrighty. Okay. Oh, we need to have the chat about the distribution vector and the powers of the transition matrix. It says here, a distribution vector is a column vector with an entry for each state of the system. It's often referred to as the initial state. And when we were talking about the initial state, it's really denoted by an S with a little subscript 0. It says here, if the initial state, S0, is an n by 1 initial distribution vector state involving n components, and T is a transition matrix, then the distribution vector after one stage is the matrix produced by T multiplied by S0. So that is the transition matrix multiplied by the initial state. So building upon that, if you wanted to find out what the distribution is after one stage, what would happen is you're finding S1, and it would be equal to the transition matrix multiplied by the one before S1, which would be S0, the initial state. Building upon that, if you wanted to find out, I'm just going to write it up here because I've run out of room, but if you're finding out the distribution after 2 stages, obviously you're looking at S2. S2 would be equal to the transition matrix multiplied by the one before, the state before that. So the state before S2 would be S1. Now, taking it further to build up some kind of formula here, consider the following. If you've got transition matrix multiplied by S1, rather than writing out S1, we had over here that S1 was equal to the transition matrix multiplied by the initial state. So rather than writing S1 here, you could write it out as the transition matrix multiplied by the initial state. If we do it that way, and we re-look at it, if I put together this transition matrix multiplied by T, so T times T, and then we've got this multiplied by the initial state over here, you can see that it's the same as t times t, which is t to the power of 2 multiplied by the initial state. And so you can start to build up this formula pretty quickly, whereby rather than having to work out the previous one and so forth like the sequence, what we can do is we can get a generalized rule or a pattern for matrix recursion relationships. So to find out the distribution after any number of stages, so n stages, you can do Sn is equal to t take away Sn take away 1, or it's t to the power of n, so the transition matrix to the power of however many stages you're after, multiplied by the initial state. Okay, so this here is really the important part of that. Again, this dot point here says if you have the sequences of states S0, S1, S2 up through to Sn, whatever number it is, that's called a Markov chain. So you're probably wondering, okay, well, where could this type of thing be used? One of the applications for this is in marketing. So what could happen is an organization could use this to predict the share of their market at any particular given moment. And the way that this could be done is, marketing records can often show when customers, when they purchase a certain good from a competing store, they can get the associated probabilities, which will see how likely they are to purchase the item again from that store or go to a different competitor and so forth and so forth. So let's have a look at this example to illustrate this a little bit. It says here, a survey shows that 75% of the time, customers will continue to purchase their groceries from store A if they purchased their groceries from store A in the previous month. Similarly, it says the records show that 80% of the time, consumers will continue to purchase their groceries from store B if they purchased their groceries from store B in the previous month. Alrighty, so it says here, how many customers are still producing their groceries from A and B at the end of the 2 months if 300 customers started at store A and 300 started at store B? Alrighty, there's a little bit to this question, so let's work through it carefully. First thing we need to do is actually create a transition matrix. So again, we had a look earlier in this example or this exercise or video on how to create the transition matrix. So you really need to extract that data from the question. So again, let's consider store A and B and where they're coming from and where they're going to. So it said 75% of the time, customers that started at store A will end up shopping at store A in the future. So we'll put the 0.75 there. Likewise, it also spoke about the fact that 80% of the time, customers who purchase their groceries from store B will continue to purchase their groceries from store B the next month. So start at store B, they'll end up at store B. So we've got those two values that are in there. Again, that was just extracting it from this information up above. We know that these unknown values that are there can be filled out by working out the column adding to 1. So actually getting the transition matrix here, you end up 0.75 as we said, you've got the 0.8. The value that's missing here, this would have to be 0.25. This one here would have to be 0.2. Next, what we're going to do is we're going to set up the initial state matrix. So initial state matrix is S0. And this is how many people in this particular case at the start were part of store A and store B. So the good news is this question says that 300 customers started in store A and 300 customers started in store B. So again, because this row here, the first row represents store A, the second row represents store B, A is going to be at the top, so there were 300 that started there, and there were 300 that started at store B here. Alrighty, we've got our information for the transition matrix and the initial state. What we need to do now is work out what is happening after 1 month, um, and see how many customers are in different spots. So let's do it for 1 month. So S1 will be after 1 month, so one state after the initial one. And to work that out, it's going to be the transition matrix multiplied by the state before that. Sorry, that's just from here above. It's going to be the transition matrix multiplied by the state before this one. So the state before S1 was obviously S0. So let's plug in these values. The transition matrix we had worked out over here. The initial state S0 we had over here, so it's going to multiply by that. And we can work that out. So working out that calculation, we get 285 and 315. Perfect. Just working over the page here, we'll now do step 2, or stage 2. So stage 2 will be the transition matrix multiplied by the stage before this, which was S1. So again, from our previous part, we had the transition matrix. State 1 we worked out just a minute ago. It was this here, these values, 285 and 315. Running this calculation, we get 276.75 and 323.25. Now, if we're talking about real people as well, obviously it's very challenging to have 0.75 of a person or 0.25 of a person, so we need to do some rounding. So the question was asking how many customers will be at store A and B after the first 2 months, which is stage 2. So we can actually now write out the answer to this question. So I'd say after 2 months, we'll round this up to the nearest whole person. We'll say there'll be 277 customers still shopping at store A. And we'll have 323 will shop at B. Cool. So let's answer that first question. How many customers are still purchasing their groceries from store A and B at the end of 2 months if 300 customers started at store A and 300 started at store B? Alrighty, next part was asking us, it says what percentage, and we're asking for in whole numbers, of customers are purchasing their groceries at A and B, so stores A and B, at the end of 6 months. And it says if 50% of the customers started at A. Alrighty, so what they've done here is they've changed the initial state. So when we've got 50% starting at store A, that means obviously 50% will be starting at store A, and the other 50% will be starting at store B. So from above, the rule to calculate this particular case, Sn will be equal to the transition matrix to the power of n multiplied by the initial state. So let's write out that formula so you can see it. Sn is equal to the transition matrix to the power of n multiplied by the initial state. So let's do that. Transition matrix from the previous question, we had 0.75, 0.25, 0.2, and 0.8. Now that's going to be to the power of n. So for 6 months, it's going to be the sixth state. So this is going to be to the power of 6. That gets multiplied by the initial state. In this case, it was 50% of customers at A, 50% of customers at store B. So what you do, you'd plug this into your CAS calculator to evaluate S6, and what you'd get is S6 is equal to 44.5982 and 55.4018. And again, you can't have that decimal number of people. So when you're writing out the nice fun sentence at the end, this is what you'd write. You'd say, after 6 months, you would have 45% of the customers will purchase groceries from store A, and 55%, round that to 55% of the customers will purchase groceries from store B. Thank you for listening up. Stay tuned for the next video where we'll continue with part B. Bye for now.